Hey, okay. Hello, Vicky. Hello, Victoria. Hello, Keon. Good. Uh, hello, Bridget. Good afternoon. Hello, Lear. Hello,
Hey,
hello.
good afternoon.
Good afternoon. Good afternoon. Hello, Aminata. Hello, Gabriel. Hello, chat. Good afternoon, Vicky, for the double. Good afternoon, Raina, for the got here very early. Thank you. Good afternoon, Victoria, for the double. Good afternoon, Sonam. Good afternoon, Gabriel, for the double. Good afternoon, Caitlin, with the emphasis. Morning, Keon, with the uh, open-mindedness. Good afternoon, Roger. Good afternoon, Aminata. I got your. Hopefully, you saw mine. The answer is yes. Uh. Good afternoon, Zoe. Oh, more people. Sorry. Good afternoon, Keon, for the double. Oh, I didn't even catch that, Keon. No, that's fine. Yes. Morning, Andy. And there's Bridget in the real life, three-dimensional. Awesome. Love it. Love it. Thank you. I won't call attention to it anymore, except that I totally will. No. Submit for points. Submit for points. Okay. Um, okay. And good afternoon, Anthony, with the picture. Awesome. Who else? We're gonna start. Hello, Anthony, for the double. And yeah, okay. Okay, we're just gonna start in a second. Um, yeah. Good afternoon, Abid. Okay. All right, I'm just gonna hop. Good afternoon, Joel. Thank you for the double. Thank you. All right, I'm gonna hop to it. I'm just gonna hop to it. Here we go. Well, okay. Um, New subtopic here, or we're just moving on in the material. Okay. Everything I'm about to say is not on a homework sheet. It won't be on a homework sheet. I mean, you're done with homework. You still can turn things in. You can still catch up, blah, blah, as am I, blah. There's no new homework questions. Everything I'm about to do now is not a homework question, but it very well could be on the final. We'll talk about that in more detail on Monday. Um, so it's important material, but it's like fresh. Okay, so just like follow along. I want to remind you of, and it's like the most interesting. I mean, anyway, I want to remind you of a couple of things to have in your mind before I do this material. So first of all, I want to remind you when I write I cross J equals K hat, that's like a shorthand way of reminding you from a couple of months ago in the semester, we got into this whole thing of dot product versus cross product. Okay, I want to just quickly remind you, right? So there was like, that was like a thing. And you may well have, well, it was a math thing that we did a couple of months ago. I want to quickly remind you of that picture because we need that picture again now. It's sort of why we did it a couple of months ago. We said a couple months ago that when vectors are involved, there's three different ways to do multiplication. Uh, you can multiply a vector by a scalar. And when you do that, and by the way, I'm saying this quickly, feel free to write this down, and screenshot the notes and get points. I'm not going to write it down because I'm trying to keep myself on task here. But, if this helps you at all, please remind yourself in your notes of what I'm saying, which is this. There's three ways to do multiplication when vectors are involved. One, you can multiply a vector by a scalar. When you do that, you always get a vector, right? Because a vector is like an arrow with magnitude and direction, and a scalar is just a arrow length. So if you multiply a vector by a scalar, what you're doing is taking an arrow and just scaling it up or scaling it down by some amount. You're just lengthening or shrinking the arrow. What you get at the end is still another arrow, right? So if you multiply a vector by a scalar, you always get a vector. That's way number one. Then way number two is you can multiply a vector by a vector in a manner that produces a scalar. That's called the dot product. And we focused a lot on that, throughout the course. We used a dot product to calculate work. The work was the path integral, it was the dot product of force and displacement, right? And then most recently, we got into all this Gauss's law stuff where flux is an integral of a dot product of field with displacement, right? So the dot product is what we use when we multiply two vectors together to get a scalar. And since we're trying to get a scalar, since we're ultimately trying to, measure the relation between two vectors that ultimately eliminates direction from the result, then when we do the dot product, we're looking at how much the two vectors agree on their direction. We're only measuring the extent to which they both fall on the same number line. The extent to which their two directions are in fact aligned, parallel, right? So the dot product is always between two vectors A and B is always like magnitude A, magnitude B times cosine of the angle between them, right? And we've used that a lot in the dot product. It's the scalar product of two vectors. But then there's this thing called the cross product, which we had to learn and which we did examples with unit vectors I, J, and K. And the cross product was when you multiply two vectors in a manner that produces a vector. When you're doing that, you're trying to preserve the directional information. You're really taking into account the directional relation between the two vectors. You're looking at how much they're not lying on the same number line, how much they cannot be treated just as two numbers in a number line. So the cross product measures perpendicularity between two vectors, right? So the magnitude of the cross product of two vectors was magnitude A times magnitude B times sine of the angle between them, right? The cross product between two vectors always produced a vector which itself was perpendicular to each of the vectors being multiplied, being crossed, right? So the direction of the resulting vector, the direction of the answer to a cross product was always given by the right-hand rule. So like if this is vector I hat and this is if this is vector I hat and this is vector J hat, if you cross I with J, you get vector K that points up perpendicular to both of those two original. Okay, now that's a reminder. We learned that. The dot product we used a lot in physics. So far, it doesn't seem like we've used the cross product so far. But we did learn it for a reason. So have it in the back of your mind for today's lecture. That's reminder number one. Oh, and sorry, good afternoon, Mohammed. That's reminder number one, just to have in your mind for today's material. Reminder number two, the electrostatic field due to a point, is given by Coulomb's law, right? And all of this stuff that we've been doing lately, Gauss's law, is all from that. Gauss's law is about calculating the electric field throughout some surface of space, some finite two-dimensional region of space. But the whole idea of Gauss's law, the flux, is that it is a quick, clever way to sum up all of the fields from all of the points um, throughout some region of space. So Gauss's law could not be true without Coulomb's law originally being true. We derive Gauss's law from Coulomb's law. Coulomb's law is the elemental, fundamental statement of how a point source of charge over here produces a field vector over here. And what I want you, right? So you know that already. I'm just asking you to remember, but I want you to now also focus on one aspect of that you might never have really thought before, which is that when we say that Coulomb's law tells you the field vector over here due to some point source over here, look at the equation. The equation is a vector field. I mean, electrostatic field is a vector, and it is a vector that can be understood to be a scalar times a vector, right? Like one way to think about the electric field is if you have a point source right here, and then you're looking at a location over here. First, you draw the displacement in your mind. You draw the displacement R vector from here to there. R vector, right? It's the distance and direction from the point source to the location. So you draw R vector in your mind. Then you say, okay, let me create a unit vector from R hat, which would be R vector divided by its length, right? So I have this little unit vector down here, a vector that has length 1, but specifically points in the direction from the point source to the location. That's R hat, right? So I think of a little R hat over here. It's telling me the direction I have to look from the point source to the place in space that I'm calculating field, right? So R hat is this little 1 unit vector pointing that way. So I take R hat and then scale it up by this combination of constants or of measurement of this combination of measurements, 1 over 4 pi epsilon naught, the amount of the charge magnitude divided by the distance, the magnitude of the R vector squared. I take all those numbers, multiply them together. That's a scaling factor. I multiply it to the R hat. I scale up R hat by that amount, and what I have is the E vector. Okay, it's just like a slightly new way maybe to look at the E vector. I want you to think of the E vector as a vector formed by one of the types of multiplication that we know. It is a vector formed by taking a vector and multiplying it by a scalar, taking an R hat vector and scaling it up or stretching it a certain amount. Okay, just have that in your mind, and have in your mind that that vector, the E field vector, is caused in the first place by a point source of charge, like just an amount, a dot, like a proton or something, a dot of charge of 0 dimension in space and of some scalar amount, like 3 coulombs. So you have a 0 dimensional scalar creating an electrostatic field vector, which can be thought of as a constituent scalar, a constituent vector times scalar. Okay, that's like a reminder or a way of looking at that. And then finally, I want to remind you last thing. So I'm just going to switch to view. Last thing that you don't know from me, but I think you know from labs, or you've been dealing with in labs, you've been dealing with circuits, I believe, where I think you just started circuits. So you've been playing, tell me if that's wrong, by the way, but you've been playing with power supplies and wire currents going through wires and resistors in the wires and so forth. So you've been looking at this thing called electrical current, just so you know that's correct, right? Or you're at least about to. If Are you playing with circuits in the lab? Could someone confirm or deny? You finished even better. Oh, okay, okay, but you did it. Okay, okay, thank you. Okay, okay. You finished, right? You guys, okay, okay, good. So great. Good, good. Thank you all. And you should submit for points. Remember, the points are still there, even if you haven't seen them in a while. I promise they're there. So submit for points on that, especially. Anyway, so current. Okay, just to what the connection between all of that? What is current? Current is dq dt. Current is you're standing at some location in a wire, some point in space, and you're counting the number of charges of coulombs that zip by you per unit time. Like 1 ampere of current from the lab is 1 coulomb per second, 1 coulomb of charge per second of time moving past a particular point in space. That's what current is. It's dq dt. In other words, current is not just the velocity of one charge moving past you, and current is not just a line of charge sitting there. Like I should say, 2 days ago, what we were analyzing with Gauss's law and all that, we were analyzing a line of charge. Seemed like we were analyzing a wire of charge. We were, but we were analyzing static charge. We were analyzing a lambda, dq dx. A bunch of charge sitting in a line is what we were analyzing 2 days ago. If that line of charge started moving past a certain point, right? If that line of charge started moving, then we'd have current. In other words, look down here in the blue. If that lambda had a certain velocity so that it was, and it kept doing that, like the line just kept going on forever and moving past us. If the line of charge were flowing past us at V, we'd have a dq dx times a dx dt, right? I mean, dx dt is V and dq dx is lambda. We would have a line of charge moving past us, dq dx times dx dt. The dx's would cancel. And so we have our measurement. We're just looking at, we're seeing how many dots of charge are moving past a dot of space per dot of time. That's what current is. 1 ampere is 1 coulomb per second. Okay. I don't know if that's a new piece of information or a reminder from lab, but I want that in your mind as we proceed. Okay. With all those things in your mind, we now get to or this point in the course, or we get to this point in history, like the early 1800s. People are like electricity is now sort of an increasingly known thing, at least among experimentalists and scientists throughout the world. Um, we have the voltaic cell. Volta invented this essentially like the cell of a battery, right? So now we have an ability to create circuit to, as you know from the lab, like volts will create amps that'll go through ohms of resistance. And we have these electrical circuits that we can play with now, as you are. So it's exciting, and people are doing various things with these circuits or these wires and these currents, throughout the world. In one particular lab, Orsted's lab, Orsted set up two current carrying wires nearby each other in parallel directions and isolated them from a bunch of other wires. So we have current one and current two going in the same direction. I don't know if they're the same value or not, but they're going in the same direction. Um, and he put them near each other. Now I should back up for a second and be clear and say, first he just put these two wires next to each other. So each wire has a bunch of protons in it and a bunch of electrons, like all materials do. There's a bunch of protons and a bunch of electrons in the wire. And he puts them near each other and they sit there as you'd expect. They don't do anything interesting as you would expect. But then he turns a switch on each one, and they're attached to a voltaic cell. So current starts flowing through each one. So now the charges are flowing through each one and flowing in the same direction, and something happens. Do you know what happens? Do you know this from other classes or from high school or or do you want to guess? I'm going to take a beat for a minute. Something happens to the two wires that he observes. I'm just curious. This is not a test, but do you know what the two wires do once there's current going through them in the same direction? Does anybody want to? All right, just acknowledge if you hear the question. You may not know, which is fine. Just make it more exciting for me. But could just anybody acknowledge that my question is, or my statement is, something happens to two parallel current carrying wires. Either if you want to take a guess in the direct chat, I'd love it. Or if you just write, someone just write in the direct chat, I understand the question. I have no idea of the answer. Oh, well, that's very interesting. Okay. Okay. Thank you. You understand the question. Okay. Okay. Fair enough. I see. Okay. Okay. Fair enough. Fair. Um, I'll go straight. Okay. I'm gonna, oh, okay. Okay, now I'm seeing a lot of answers. Okay, okay, okay. Wow. So you guys do know. All right, all right. I, I'm going to address. I mean, there's something in there's a couple in the public chat. I'm definitely going to address those, and I appreciate. And by the way, I appreciate that. All of you who submit, please screenshot this and submit for points. You get points for participating, and some of you really want the points at this point and deserve them. Um, so I'm reading everything. I want to acknowledge directly the thing that was said in the public chat. In 1 second, I will. Here, okay. Should I read that? Well, I'll just read. Here's what I have. What I have in the direct chat is, yes, I understand the question. I don't know what happens, but I understand the question. I understand the question, thinking on it. Cool, cool, cool. I don't know the answer. Cool. I told all that stuff really does help me. But then I'm seeing in the direct chat also, they attract each other is one option. They attract each other, which causes a magnetic field is another option. Maybe they do static electricity is another thing I'm reading. Does the current split? That's interesting. I mean, it already sort of is split. It's two different currents, but that's an interesting thought. Another person I understand, and I'm ignoring. And then in the public chat, as you see, someone wrote something about magnetic field. Okay, these are great answers. They're sort of all right, actually, in a way. I want to leave. Okay, here's what the answer is. What they observe what they observe is that the two wires attract each other. That is the observe. That's Orsted's finding. What he finds, what he sees, what sort of what he sees is they attract, like they pull towards each other. Okay. That's what he sees. Now, I'm not ignoring the person in the public chat. Well, Keon, I mean, it's public. I'm not ignoring Keon who said something about the magnetic field. I'm actually very excited and impressed that he said that Keon said that. And other people like made that reference in the direct chat. I'm not ignoring it, and I'm definitely not disagreeing with it, but I'm going to postpone it for a moment. Okay. Let me first start with what they notice, what Orsted, and then tons of other people in other labs notice is that the wires come toward each other. Okay. Now, in a way, and somehow try to take notes on this. Okay. I mean, I will give you more notes in a moment, but anyway, in a way, this is not surprising at all. Because if it were a total surprise, they wouldn't have set this whole thing up. Like they, of course, were trying to isolate the wires and be very careful and get them near each other. They were looking for an effect. They, of course, had some reason to expect or hope that something interesting was going to happen. And furthermore, they might have even had some reason to believe that something was going to happen over this empty space distance between the two wires. Like, yes, they had some reason to suspect that perhaps one wire would affect the other through empty space without touching it because this is what we've been seeing protons and electrons do now, for years. We have a whole theory around how electrons and protons do this. They attract each other at a distance. So in some ways, there was an expectation that something was going to happen. However, what's very weird, what's very surprising, and a very big deal is the direction in which something happened. What's weird is that these two wires came closer to each other rather than going away from each other. Why is that weird? Well, because masses do that. Masses pull on each other through empty space and come together through this action at a distance called gravity. But gravity is not the explanation for what's going on here because this wasn't happening when the switches were off, right? When the bunch of protons and electrons were just sitting in the wire, they all had a bunch of mass and stuff like that. But evidently, the gravitational force wasn't strong enough to overcome whatever was holding the wires together. Like the gravity didn't do anything when the charges were just sitting in the wires, and gravity doesn't care whether you're moving or not. So when the current was turned on and the wires came together, that's not gravity. Because if it were, gravity would have been acting even before the charges were moving. So it's not gravity that's doing this. So then you might say, well, duh, of course, like, come on, get to the chase. Like, obviously, we're talking about charges here. We're talking about electricity. So this is an electrostatic attraction. Duh, like, what is this even interesting? But think about this. First of all, again, when the switch wasn't on, when there was no current, there were a bunch of charges in the wire, and this wasn't happening. And it shouldn't have been happening because even though there were a bunch of protons in this wire and a bunch of protons in this wire, there was an equal number of electrons in this wire and in this wire. So whenever the protons here were attracting the electrons there, they were equally repelling the protons there, right? When we turned the switch on, we didn't add any more protons or add any more electrons to either of the wires. We just set the electrons in motion. There's electrons in motion now in the top wire and electrons in the bottom wire now. They're in motion. You might say, okay, because they're in motion, somehow there's like more of them, like because they're moving so fast, maybe they're clumped together more or something. So you might say, so I guess there's an extra net charge somehow because they're moving now, like maybe something like that. But the key point is if there's extra electrons now in the top wire because of the motion, then there's extra electrons in the bottom wire because of the motion. And you know that like objects repel. Like if this were electricity, I mean, if this were an electrostatic effect that somehow arose because we turned on the currents, if it were explicable by the field that we already understood, then the wires would have repelled, but they attracted. And that's so surprising and so weird that they even tested it the other way. Hold on. When one of the wires was turned around, it repelled the other wire. So direction definitely mattered. Direction definitely mattered. And there's definitely action at a distance here. But the action at a distance is not explicable. Is not you can't explain it by looking at what we know of gravity, nor looking at what we know of electrostatics. In other words, and again, well, in other words, Okay, what I'm trying to emphasize is that this is action at a distance. One wire is affecting the other wire through empty space. Anything that affects something else through empty space, action at a distance, we ultimately understand as a field. Like that's the whole point of fields. It's that. It's action at a distance. This is a field happening here. But the mere direction in which it's happening, the mere fact that it's attraction between like currents and repulsion between unlike currents means it's not a field that we already understand. It's not one of the two fields that we already understand. It's not gravitation nor electrostatic. So it's some kind of new field. I'm not new to the universe, but new to our understanding. Uh, this new field that must explain this it must mean, in other words, that there's some kind of field like when a mass is sitting around, it creates a gravitational field. When a charge is sitting around, just like existing, it creates an electrostatic field. What this seems to suggest is that when a charge is moving, it creates a new, different type of field. Like in addition to the fact that there's already gravitation and already electrostatic, when a charge or a bunch of charges are in motion, they create an independent third type of field. No one had ever analyzed it before. No one had ever done math on it before. They could have called this field anything. They could have called it the Oersted field or the Yaverbaum field. I wouldn't suggest it. But they didn't. Here's where we go to the Keon point here, and some other people in direct chat. They could have, this is a discovery in the mid 1800s of a third new field. They could have called it anything, but they realized, wait a second, we're about to start analyzing and mathematically unpacking a field that we never have before. And they realized, and this is involving like charges moving through the only type of material they can move through, metal conductors, right? So they realized, wait a minute, they're actually in the world, in the regular sort of non-physics world, there's been an action at a distance that has been observed for millennia, that everybody's used everywhere, that no one has ever mathematically analyzed or given any kind of underlying microscopic reasoning for. But everybody in the world knows that certain kinds of metal, when you put near other kinds of metals, the same kind of metal, like if you put a hunk of iron near another hunk of iron, if you put them one way, they seem to attract. And if you turn around the other way, they seem to repel, right? And if you take little slivers of iron and you put them one way, they seem to be attracted to the iron core of planet Earth. And if you put them the other way, they seem to like swing around and be repelled by the iron core of Earth. And we call these hunks of iron that seem to attract and repel when you orient them certain ways, we call those magnets, right? And everybody's used them for millennia. Like, in fact, there's been some sort of basic operational understanding of magnets that far preceded anybody's operational understanding of gravity. I mean, in a way, that's kind of a stupid thing to say, but the point is, people have used hunks of iron to play with and to build compasses from and navigate the seven seas. For literally millennia at this point. No one has a mathematical understanding of magnets. No one has ever analyzed them in terms of field or field lines or field equations or anything like that. But people have been deploying the action at a distance known as magnetism forever. And everybody knows that it's somehow associated with metals, certain types of metals. So these guys, Oersteds and others, and Biot and Svar and Ampere, they sort of take a conjecture or a hope and say, so this is the Keon point now. I'm coming at it from a purposeful direction. They say, oh my God, there's some kind of action at a distance that we never knew about before. An action at a distance between moving charges, which we were never in a capacity, we never could study before until we got to this technological point of being able to set up flowing currents through wires with voltaic cells. Now that we can like look at currents and isolate them, in the earlier mid 1800s, we're noticing that flowing charges seem to create a field, seem to interact with each other through a distance, and it requires metal to do this. So we're going to take a leap and say, I wonder, so this is some kind of field that we're going to now start analyzing. Let's hope, in the matter of physicists who are always trying to understand the greatest number of phenomena possible with the fewest pieces of information or the fewest principles or the simplest rules possible, let's sort of hope that whatever this is that moving charges do, whatever this field is that moving charges create, let's sort of hope that that is ultimately responsible for the fact that hunks of iron attract and repel other hunks of iron. And so, therefore, let's call this new field the magnetic field. Okay. So, in other words, I'm totally agreeing with Kian. Thank you. And agreeing with some of the other people in the direct chat who posited that or speculated. Like, good answer. Okay. So good, like, yay. Like, seriously. But I want to tell you like why it just took me so long. I could have just said you're right from the start, right? But it didn't for a reason. Hold on. Okay. I'm saying number one. Well, okay. So, so again, so like I'm totally saying so those of you who said that the two wires attract each other, totally correct, and thank you. And then those of you who said magnetic field or something, correct, clearly correct. So thank you. I just wanted to sort of get the sequence of the thoughts arranged properly in your mind. Like, because this is I just want to make it clear that what they saw in the observation is attraction. The observation is, ooh, action at a distance here. Didn't see that come. Like action at a distance between moving charges, something that we could never have specifically seen before because we couldn't get this. We couldn't isolate, control, and create charge flow. Like we didn't have electrical currents before the mid 1800s or the early 1800s, late 1700s, right? So for the first time in history, we're looking up close at charge flow, current. And now we see currents create action at a distance with and interact with other currents. So we say for the first time in history, oh my gosh, currents create a field. We then link that in our mind to this action at a distance that we've always noticed in macroscopic metals. Like again, I'm just sort of trying to say, like, nobody that was making compasses with little iron pieces knew about electrical currents, right? We're saying the fact that we need metals to make electrical currents and the fact that electrical currents seem to affect each other through empty space means there's some kind of field here. Let's hope that this field here is somehow the same field that seems to be acting when hunks of iron macroscopically attract and repel other hunks of iron. That's not self-evident. It's not obvious that that's the case, but that's sort of the hope of this. And it does turn out to be true. So we're sort of trying to explain two unexplained phenomenons. Now that we have a field way of looking at the world, now that we have this fleshed out notion of field, we're sort of hoping, oh, or we're sort of now that we've discovered that moving charges seem to create a field, we're like, oh, What if the field that's created by moving charges is the field? Basically, we're saying, oh, what if the moving charges, what if metals like iron create a bunch of, I mean, contain a bunch of moving charges in them, and that's why they attract one another. Then this is all one and the same phenomenon. So we're going to give it one name and say this is the magnetic field. Okay, like that's like the thought. And I see that there's something in the chat. Well, let me see what's in the chat. Hold on. Oh, no problem, no problem, no problem. But thank you. Well, actually, let me cut to the chase to really to clarify this, and then I'm going to go. So I have to do the math. Oh, and this magnetic field, for a weird historical reason, at the risk of confusing you, the magnetic field, like electrostatic field, is designated capital E. Gravitational field is designated lowercase g. The magnetic field is designated capital B. Don't ask why. I mean, it's for a historical reason. It's a little confusing, but just please accept it. The magnet from now on, if I ever say B, I mean the magnetic field. And of course, I'm always going to put an arrow over the B because, like any field, B is a vector. And field, from now on, I'm going to say there's this that magnetism is a field, which means it's got to follow all of the rules and techniques and drawing uh, methods that any other field does. Like the whole idea, this is like physics thinking. We've already nailed down this whole framework called fields that applies whenever there's a action at a distance phenomenon. So now we have a new action at a distance phenomenon. Let's call it a field, and let's assume that all the notions of field apply to it, like until that gets us into trouble, which it won't. Um, Quick aside, or quick thing to close this loop. All objects have a bunch of protons and electrons in them, right? And if, as you know from chemistry, and all objects are made of atoms, which you know from chemistry, in an atom, like the protons are sort of sitting there in the nucleus, more or less, sort of heavily, but the electrons are whizzing around, moving in the orbitals. So is every single atom has moving electrons in it. Every single atom is a little circuit. I mean, is a little current loop, if you think about it. Like automatically, naturally, there's electrons flowing around and around. So there's a current in every atom. So every atom, if this is right, and it is, like if currents create magnetic fields, then every single atom creates a little magnetic field. But in most materials, all the atoms are just like randomly aligned. Like you'll have an atom going like this, and another atom going like this, and another. So in most typical macroscopic materials, all the little magnets within are all canceling each other out. They're all going in random directions and canceling each other out. So the net effect of any random material is that it doesn't generally create any net magnetic field. But in some objects, certain metals like iron, because we can move the electrons around, because the in metals electrons, because metals are conductors in certain, and so in the conductors electrons can be moved around. It turns out that in certain metals like iron, the orbitals of all the electrons can get very easily lined up. So what makes iron iron is that it has all these electron orbitals, but they're all sort of going the same way, like orbital, 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 orbital. So they're all reinforcing each other. They're all these tiny little magnets that instead of canceling each other out, are all reinforcing each other. And that's why, in the end of the day, a hunk of iron is like a big coil of wire around a toilet paper tube or whatever, and makes a magnet. I mean, that's kind of an aside, but just to that turns out so what we're in now I want to study how the magnetic field works on the elemental level, but indeed it's called the magnetic field because ultimately it explains what's happening macroscopically with compasses and iron filings and everything. Okay, so the question is, So we're now in a position, we already know how fields work. We know how the gravitational field works. We know how the electrostatic field works. And when I say work now, I mean mathematically. It like look at the form of the field function for electrostatics. It's a constant times it's a constant first, a proportionality constant, right? That we just need that just makes the units work out. And that would be a different constant if we wanted things to work out in different units. But there's a constant first. But then there's the thing, there's the source that okay, huh? Okay. Just I'm trying to remind you, the electrostatic field function. Yeah, I guess I can't deny I have to draw a picture. Okay. I'm trying to remind you once again that with the whole electrostatic field function, the idea is that you have a point source Q, like over here. You are trying to figure out the field at some other location, call it P, over here, right? So in your mind, you draw a displacement vector from Q to the point P, right? And then you create a unit vector from that that just captures its direction. And then you scale up the unit vector by this amount, 1 over 4 pi epsilon naught Q over R squared. And that creates the red final, the E vector that's at the point P. In other words, part of what I'm trying to say right here, I'm trying to really emphasize, is that the field vector E that is existing at the point P is a scaled up or scaled down version of R, where R is the displacement from Q to P. The direction of E is in the direction of R. Like that's what I'm trying to emphasize. That R is really important. If we didn't know R, if we didn't know the magnitude, we wouldn't have an R squared in the denominator to divide by. And if we didn't know the direction, we wouldn't know the direction that the electric field and therefore the electric force would point at P. The direction of E is the direction of R. They're the same, so it almost seems like we haven't said anything, but we wouldn't, but we need the direction of R to get the direction of E, is what I'm so if if B is going to follow the same logic. If it's a field, it's going to follow field logic. It's just going to be based on the situation that we now have. What is the situation that we now have? The situation we now have is not just a charge, but a charge with velocity, right? In order to create the magnetic field, we need not just a charge, but a charge to be moving, evidently. So it's a charge that has some velocity. And we're at some point over here, P, right? And again, we're going to have an R that points from the moving charge. We're going to have a displacement that points from the moving charge to our location P. And again, the unit vector R is simply the displacement R divided by its own magnitude, right? It's all the same deal. So we're going to try to build a field from that set of facts. Um, well, first of all, for B, there's going to have to be, sorry, there's going to have to be a constant at the beginning, just like there was for E, but it's not going to be the same constant. If we're following the same model, there's going to be a 4 pi involved because we're going to, if fields are fields, they're going to spread out infinitely in all directions in the same way in all directions like the surface area of a sphere. So there's going to be if we're following the same model, we're going to assume that the same kind of cancellations are going to have to happen. So we're going to want to have a 4 pi in the denominator just like before, and there's going to be a constant like epsilon naught, but it's not going to be the same constant because it's now magnetism. And since the constant we can define any way we want to make this all work out, we now have the luxury of starting afresh and putting the constant on top. Like we could define it so that it's on the bottom, like we discovered before, but that's awkward and annoying. And we now have a chance to calibrate our own function. So we'll say this. Like so I'm saying there's a constant, just like the other, but it's a different constant. And here this number turns out to be, you don't have to memorize this or anything. I'm just telling you. Um, and then in the numerator, of course, the thing that's causing the charge, um, excuse me, the thing that's causing the field has to be in the numerator of the field function. What's causing the field now is not just a Q, but it's a QV, right? In the denominator, well, yeah, and in the denominator, we're assuming fields are fields that they spread out evenly in all directions, whether it's gravity or electrostatics or magnetism. So in the denominator, there'll be an R squared again. Like this is what we discovered last week, that it's not a coincidence that when something creates action at a distance, it creates it in an inverse R squared way. So we assume there's an R squared in the denominator. Um, and what has to come into play is that R hat, the field has to have some direction. So it's going to be based on the direction from the point source to the location of interest, right? So this is what we're building. These are all the elements of the equation that we're building so far. I'm just going to recopy on the next page. Right? This is what we have so far. But here's it. And again, this is just assume if there is a field and we're calling it magnetism, if it's truly a field, the assumption is it's got to work the way fields work. But this is a field now that's being caused by not a sitting mass, not a sitting charge, but a moving charge, QV. So these are the elements that are contributing to the mathematical formulation of this field. But but Like now there's a big difference. R hat was always a vector and was always in the field function, whether it's electrostatics, gravity, what. R hat is the unit vector that points in the direction from the thing causing the field to the place experiencing the field. That's information that is definitely determining the field. But there's now the thing causing the field is itself a vector, right? It like what like none of this happened when the charges were just sitting in the wires and the circuits weren't on. It didn't happen. This field did not come into being until the charges started moving. So they had to have some kind of speed for this to happen. And apparently it mattered what direction they moved in. When the wires were like this, they attracted. But when we turned around one wire, then they repelled. So it's not just the speed, it's the direction of the charges that's determining this, i.e., it's the velocity of the charges. The thing that's causing this in the first place is itself a vector pointing in some direction. I don't, it could be pointing in any direction, right? But it matters what direction it's pointing in, right? So So now we've got two vectors being multiplied by each other to determine the final vector. We've got two pieces of information contributing to the field vector, and the two pieces of information now are both one-dimensional vectors rather than one of them being a zero-dimensional scalar. Now there's right? So we've got a vector multiplied by a vector to produce a vector. It's only one way to do that. It's got to be what kind of product? You tell me in the chat. If this is a vector times a vector to produce. Nice. That was fat. Oh, he's on fire today. Keon's on fire. Yes, absolutely. I'm not even waiting for anybody else. This must be a cross. That's really good. You should definitely submit for points, please. I'm saying that apparently, now, maybe this is part of why the magnetic field is designated with a B, because this law is called the Biot-Savart law, like they're French, Biot and Savart. Um, um, so this law is to magnetic field as the Coulomb's law is to the electrostatic field. Like this is the elemental construction of the field contribution, but it has a cross product in it, and that's very heavy. That's a very strange thing. I mean, it's a very unexpected, unusual. We've never, well, somebody explain what I mean. There's a cross product now. You remember the cross product produces a vector which is whose direction is determined by the right hand rule. What this means is that the B field produce a charge is moving along, and you ask what a charge is moving along like this, and you ask what's the field over here due to this moving charge. There's going to be a field vector over here, magnetic field vector. What this math says, what this just says, is that the direction of the B field over here points along an axis that is not the axis of R and not the axis of V. The B field points in a direction that seems to have literally nothing to do with any of the information that's producing it. What I specifically mean, it, what I specifically mean, it does not act like the E field. I specifically mean, if you go to the original example that's creating all of this, or this example, if you look at these two wires, well, all right, let me just draw a new picture. Sorry, hold on. We have 10 minutes. If you think about one of the top wire in that original experiment, charge is moving along like this to the right, and you're down somewhere below at point P, and you're like, oh, there's a magnetic field produced by that wire above, right? You're down here at a displacement R from the wire. So at the point P, if I want to know what the B field is doing, I apply the right-hand rule to this Biot-Savart law right here. What I do is I take my right hand, I place my fingers along the direction of V, I curl my fingers down the direction of R, uh, and the B field at P points in the direction of my thumb, right? Right hand rule. But I'm backwards because of the screen. It's confusing even me. Well, no, yeah, right. Okay. So I go like right hand rule. Fingers along the direction of the V, curl down in the direction of R. My thumb points into the screen. If you think of vectors as like medieval arrows, if an arrow is coming toward you, you would only see the tip of it. But when the arrow, okay, so this is how we draw these things from now on. Sorry. If something were coming at your eye, you would just see the tip of it, a dot in the center. But if something were going away from your eye into the board, you'd see the cross section of the tail feathers, right? So from now on, an X means into the plane of the board or the computer screen or whatever, and a dot means out. So I'm saying that the magnetic field here at point P points in to the board. Unlike the E field, in other words, we're down here under the wire, you'd think that the field would like push down or up, especially since the other wire gets pulled up, but it doesn't. Or then you might think, well, I guess it points in the direction of the speed. No, it's pointing in the direction that has nothing to do with the velocity nor the displacement. Because if it had something to do with either one, it would be giving more weight to that information in the field calculation. In other words, at that point P, what space knows is that there's something up there that is going like that. And if space is going to know that there's something up there going like that, both those pieces of directional information are taking into account, and neither one is being taken more into account than the other. So the way to give them both equal treatment is to have the results spat out on the third seemingly irrelevant, but in fact independent axis. The B field points into the plane. So then you might say, well, how does that make any sense? Like, well, how does the other wire then get picked up if the B field is pointing into the plane? Because we have 6 minutes left. Yeah. Okay, remember, we got 5 minutes. This is a fast in. This is not going to take long. Um, Remember, field in the first place is force per charge. So force is field times charge, right? Like you want to know what's happening to, so a source charge over here creates an electrostatic field. Then a test charge is in that field. It experiences a force. The field times charge equals force. Well, same thing here, right? A moving charge will create a magnetic field. In order for something to experience the force from that magnetic field, it itself must be a moving charge, right? So, in the same way that electrostatic force equals electrostatic charge times electrostatic field, similarly, magnetic force must equal moving charge times magnetic field, right? Same thing. But again, we have two vectors being multiplied together to make a vector. So this must be a cross product as well, right? So we have 4 minutes left. So so the field is created by a right hand rule, but then the force due to that field is created by a right hand rule. So the charge moving this way, the charge moving this way, if I look down here, creates a field that's into the board. Now there's a field into the board, and now there's charges in that field moving this way. So now I apply this law to see what happens to them. I've got charges going like this, but in a field that's pointing into the board. So I'm doing right hand rule. Put my fingers on V, they're going to the right. They're in a field that's pointing into the board. So I'm crossing them. So the force is what my thumb is doing up, right? So they get pulled up to the top wire, and that's how it works. That's why Orsted found what he found. It's a very strange thing. So in other words, the top wire creates a field, the bottom wire experiences the field, the bottom wire gets attracted to the top wire, but the field the whole time is at this cockamamie angle at right angles to the top thing. There's one last thing I have to say. The right hand rule apply. There's 2 minutes left. And this is the last thing I'm saying, but it's super important, of course. The right-hand rule applies to every point in space. So imagine one wire for a second. One wire up below going like this. If you look below it, the right-hand rule says field is going into the it's going like this. It's going into you, right? But if I look above the wire, right-hand rule, I curl my fingers up, then above the wire, the field is going back the opposite direction. If I were to look in front of the wire, right-hand rule, the field would go up. If I look behind the wire, right-hand rule, the field would go down. In other words, wherever you go around the wire, the field vector, if you think about doing the field vector anywhere around that wire, the field vectors are all looping around the wire. In other words, right? So in other words, what I'm saying is B field lines always, like they're following all the rules. We're following all the original rules of fields. We're following, oh, actually, it's 130. So here's the conclusion. B field lines always form closed paths. B field lines loop around straight currents. They're following all the rules of fields, but following the rules of symmetry and asymmetry that would be produced by a flow of moving charges. B field is a simple as possible result of what would happen if a one-dimensional vector produced a field rather than a zero-dimensional scalar. And the result of that is that whereas E field lines burst out from points, B field lines loop around lines. That's the bottom line. You've been very patient. Classes. See you. See you soon. See you. See you Monday.